Okay, so we're gonna start with chapter 4 of Sontag, which is work and heat. Okay, work and heat. So in any study of thermodynamics, it is important for us to understand how a system will interact by exchanging heat and by doing work. And the simplest definition of work, and rather than saying the simplest definition, but the most concise definition of work is equal to the integration of F dot dl. So it is the component of force which causes displacement along dl, and dl can go along any length. Okay, so it's basically the force in the direction of the displacement, and this is something which you might have learned in class 6 or whatever, whenever you are being taught all of this. Okay, so it's not just restricted to work done by pressure. It could be work done by a charge moving in an electric field, or charged particle through a magnetic field. It could be the work done to increase the area of a film, as we have done in the fluid mechanics course for surface tension. It could be many things. Okay, so how do we define work? Work is done by a system. So let me write it down. Work done by a system when the effect of this can be used to raise a weight against gravity. Okay, so it can be used to raise a weight against gravity. So it could be like, we can have an example. I mean, we have a battery. Battery has two terminals, and we can have a small DC motor, and you can connect it like this, and say there's a, I mean, let's say this is the shaft and this is the only system. So if we control this as the control volume, the moment the motor shaft is rotating, we say that work is being done by the system. And why is that? Because we can imagine a pulley over here and a rope. So it can be connected to a weight, and you can imagine that this rotating shaft could be somehow used to raise the weight against gravity. And so we say that the system is doing work. Okay, so I mean, this is quite obvious. There's nothing very difficult about this, but just a bit of convention is there that work done by a system is considered to be positive, and work done on the system is considered to be negative. And work is something which is in transit. Okay, it is the energy which crosses a system boundary. All right.
Excuse me, sir. So I did
Yeah.
not get like how you told just right now. Energy.
So if you have a system which you think has certain amount of energy, if you want to transfer that energy to something, you can do it through work and heat. Either you can perform work so that the work is performed at the expense of the energy held by the system, or you can transfer heat. So the transfer of heat is also at the expense of the temperature of the system. So work done, you cannot say that this system is holding a certain amount of work. No, that is wrong. It can hold a certain amount of energy, and to release or gain more energy, you must either transfer heat or do work. Okay? So work done
Yes,
and
sir.
heat, they are things in transit. You cannot hold heat or you cannot hold work. All right, so let's proceed. Let me just get rid of this. So the units of work, obviously everyone knows that work done is measured in joules, and because in thermodynamics the quantities are quite large, you will most of the time encounter things like kilojoule. The unit of power is watt. Okay, that is joule per second. Basically it is joule per second. And typically, because the systems are going to be large, you will most of the times encounter kilowatt. And so what is horsepower? Have you heard of the term horsepower?
Yes,
You might have
yes,
heard it.
sir. Yes, sir.
Yes, sir.
So horsepower is an English unit, and typically we will avoid using non-SI units in our work. But a horsepower is 746 watt. Let me just verify that. Horsepower is 746 watt. Yes. Okay, it's 746 watt. But more precisely, a horsepower is an English unit, is an imperial unit, and it is 550 foot pound force per second. So, okay, so this is what it is. And just on a light note, let me just show something very funny. I mean, you should not take whatever fun things I say and take it out of context. So, just so it's a very funny. I mean, I wouldn't call it a meme, but hmm, it has become one. So just let me put it over here. So the Americans, they are notorious for not using the SI units. So this is one of the there's an entire section on Reddit which says Americans will use anything but the metric system. So a sinkhole roughly the size of 6 to 7 washing machines has closed the northbound lane. So Americans, whenever you're dealing with uh, American textbooks or something, you will find such foot-pound force per second. I mean, it's very, very weird and obscure units. But yeah, this is what the thing has boiled down to. Okay, so let me just get rid of that image. Let me just close the door because a lot of sound here. Okay. All right. So now we will move on to the idea of a simple compressible system. I mean, we've discussed this, but we will now study the work done at boundary for a simple compressible system. Now, let's imagine the simplest system, something like this, and you have a cylinder and you have a piston and you load it with a certain amount of mass. So the system at this juncture, so this is the control mass is this, the red boundary will be the control mass. Okay, so this is the control mass and this is at a certain pressure and it has a certain volume. Now when this weight is removed, what will happen? The piston will go up because you have reduced the amount of pressure acting on the system, and so the system can push the piston upwards. Consequently, what will happen is the pressure inside will drop. It will come to the equilibrium pressure. So you have removed one of the blocks. So at this juncture, the pressure has reduced. So if I call this P1 V1, this will become P2 V2. So here V2 will be larger than V1, but P2 will be less than P1. And P2 is less than P1. Why? Because the external loading on the gas has, or the substance has reduced. So if I were to keep doing this, eventually it would keep going up and you will reach a certain equilibrium again. And remember, removing these weights in order to affect a reduction in the pressure is done slowly, so that at each step we can assume that the system is in equilibrium. Now if I were to plot all of this, if I were to plot all of this, I would have the following. So you would have a certain process like this. Well, you cannot say for sure what the process is, because I have not specified whether this cylinder is insulated or whatnot. So say that through experiments you have obtained this curve, and over here you have pressure, over here you have volume. Okay, so this point is P1 and this point is P2, this is V1 and this is V2. And this is what it is. So now let us try to find out the work done at this boundary. Okay, the work done at the boundary. So the work done when the pressure is P, when external pressure is P, right? Or rather, not when the external pressure is P. We can say at a certain point, suppose pressure is P, and so P is both because of the weights outside, and so by equilibrium it is the pressure of the substance inside as well. So the pressure is P. Now you have affected the external pressure by removing a very small amount of mass. So then second step is remove small mass, so that the internal pressure at this point is larger than the external pressure instantaneously. So P in will be larger than P out. I mean, the difference is small, but instantaneously this is true. Then what will happen? Because of this differential in pressure, the internal pressure will push against this uh, piston assembly, and say piston is pushed, piston is pushed by a distance dl. Okay, the total force acting on the piston will be equal to the pressure times area, and so the work done by the internal gas, by the, no, I'm calling it gas, but the internal substance is gonna be this. This is the work done by substance. And so after doing this work, what will happen? It would have moved by a certain distance and the pressure would now become equal to P out again. Okay, it cannot stay P forever. So this is the differential work. You must realize that this is only the differential work, meaning for a small displacement at that pressure, this is the amount of work that is done. And so the total work done in going from state 1 to state 2, will be the integral of P A dl, and when the area is constant, you will have this as integral P dv. So this is the total work done by the system. Okay, in going from state 1 to state 2, in going from state 1 to state 2. Okay, so this is quite simple, and you must now know how does pressure change with volume. You must know this information in order to perform this integration. Now, like I said, This could be obtained experimentally, or you can approximate this to be a certain process. So this curve, it can be known experimentally, like they used to do for calibrating the automobile engine pressure versus displacement curves, or you can do it, you can assume a certain model. And you have done this, I know you have done this in JEE, but still I want to repeat that. So for an ideal gas, say suppose we are dealing with an ideal gas, what is the work done by a gas when it expands from volume 1 to volume 2 in an isothermal process? Suppose someone asks this, isothermal process. What is the work done by an ideal gas in an isothermal process? So W12 will be integral PdV in going from 1 to 2, and we know that for an ideal gas PV is equal to nRT. So we can write this as integral nRT over V dV, thus yielding the very famous result nR bar T ln V2 by V1. Similarly, you can figure out for an ideal gas W12 in a polytropic process. So what is a polytropic process? It is a process where PV raised to some constant n, and this is equal to constant. When n equal to 1, we say that the process is an isothermal process. So in this case, integral PdV, very simple to find out, and you can do it. It's very easy. So it will be P2V2 minus P1V1 over 1 minus n. You can easily verify this. So you must know what kind of process is going on. Otherwise, you will not be able to perform the integration. Okay. So let's move on. So let's go beyond this and consider an important concept. This is still not gone. This is still there. I thought we got rid of this. No disrespect to the Americans, but yeah. So where was I? Yeah. So right now we're gonna, and we have looked at parts of this. So a very important class of problems that you will experience throughout this course is a piston cylinder arrangement with a spring. Okay, we will consider a piston cylinder arrangement with a spring. And why is this important? Because in many of the processes, in order to have a control on the expansion of a piston cylinder arrangement, it's most common in cars or compressors. It is found most of the places. You will have a spring so that the expansion of the piston is not, it's not withheld. Rather, it's not free. It is withheld by something. Meaning, let me just draw the diagram. It should be clear. Oh, this is not. This is a select tool. Okay. You have a cylinder like this, and the cylinder will have a small bracket at the end. Cylinder will have a small bracket at the end, and you will have a piston over here. So this is now a piston cylinder arrangement. But when the gas is heated or the gas is cooled, suddenly the piston will have, the piston is relatively friction free. So it can go all the way, and it can, if this stop is not there, it can actually exit. So there are two things that you will notice in most of the problems. Either it has a set of stops. So this is just machined in the cylinder so that this piston cannot fly away. It can at best go to this resting position. Apart from having stops, what you can also have is a linear spring. So when this piston goes up, that is when the substance inside expands, when there is some kind of expansion going on, this progressively the force acting on the substance will increase because you're compressing the spring. When you compress the spring, Depending on the degree of compression, you will have more force, progressively more force acting on the spring. Okay, so now let us consider the analysis for such a system, and this is quite important. You will find this in many problems. So when the piston is in equilibrium, piston is in let's say that the piston is not in equilibrium, then what would you do? Let's say that the piston is not in equilibrium, the mass of the piston is m, so we call it mp. So mp times a, this is the total mass times acceleration of this piston. It will be the sum of all forces acting upwards minus sum of all forces acting downwards, and this is just convention that we are considering the coordinate to be upwards. Okay, now what is the ramification of assuming that the entire process is quasi-static? What is the ramification of this assumption? Quasi-static, quasi-stationary?
The upward force will
Hmm? Yes, tell.
upward force will be
No, if we say that something is quasi-static, then it means that there are no sudden movements, no sudden changes. But no sudden changes does not mean that there is no change. It simply means that the acceleration would be zero. It would go slowly, that this acceleration would be very small, and ideally it would be zero. Okay, so this is approximately zero because of this assumption. It will never be zero. Of course, it will accelerate, but at some absurdly small speed. Okay, do you understand? So 0 is approximately equal to sum of all forces acting upwards minus sum of all forces acting downwards. So what are the forces acting upwards? So the forces acting upwards on this particular uh, piston is due
pressure
to,
times area.
so it will be the pressure times the area. What are the forces acting downwards? Now the
Spring force and mass.
so let us divide it into spring force, and mass. Okay, this is it.
So one doubt, sir.
Yeah.
So what was the difference between quasi-static and reversible?
Reversibility comes through the ideas of entropy. So we have not yet, I mean, there's plenty of time to go to that state. So reversible has a very distinct uh, definition. It's not just what you use in common language that this is reversible. No, it has roots in entropy. Okay.
Okay.
All right. So let us say that apart from this, there is always some point force F1. This is just, I mean, just to make this derivation very generic. Okay. So the total downward forces will be due to the spring plus the mass of the piston itself. Then there will be atmospheric pressure, and what else will be there? There will be this point force. Any other external force, I mean external force. And in this case it's a point force. So this will be equal to the spring constant of this spring times x minus x naught plus the mass of the piston times the gravity plus the atmospheric pressure, because this is open to the atmosphere. So there is always atmospheric pressure acting all over the top surface of the piston. So P naught times A, right? And the external point force. This could be any other external force as well. All right. So when this is the case, okay, so what is x naught? X naught is the relaxed length of the spring. Alright, so when we equate these two, we have P times A is equal to P naught times A plus mass of piston times G plus F1 plus spring constant times X minus X naught. And so therefore, under this quasi-static approximation, we can say that the pressure can be related to all the external factors as P naught plus mass of piston times G over A plus F1 over A plus Ks over A x minus x naught. And over here I can multiply and divide by area on this. So we will multiply A to both numerator and denominator of this spring force, and therefore we will obtain P naught plus mass of piston, the pressure due to the mass of piston, plus the point force, plus Ks over A square times A x minus x naught. And therefore uh, this particular term this particular term is fundamentally Ks over A square times, so area times the displacement is like the volume minus relaxed volume. Okay, V naught is equal to volume occupied by the substance by substance at relaxed condition. All right. All right. So finally, the result of the derivation is, so before going into that, let me just mark this. So the blue term, the term outlined by blue, that is always going to remain a constant. So this will always remain a constant because the external pressure is not going to change. Typically for experiments we do on Earth, this can change if you are like taking this piston in a spacecraft and taking it to a very high altitude. This will change, and how it changes, I think I might have covered it in the fluid mechanics course. But even if I've not covered it, you can imagine that it changes. The pressure, the ambient pressure reduces as you go higher. The mass of the piston is not going to change. The area is obviously not going to change. Gravity is not going to change unless you go to a higher altitude or a deeper depth. The point force that we are applying, it's not going to change. By definition, we are applying always a certain amount of force. So this is some constant which we term as C1. Now the spring constant, ideally it doesn't change. The area is obviously not changing. So this can also be treated as a constant, C2. Well, not just that. So if I write this as C1 plus Ks over A square times V minus Ks over A square times V naught. This Ks over A square times V naught is also something which is not gonna change, because X naught for a spring is always fixed. Correspondingly, V naught will also be fixed, and therefore this is also a constant. So we can absorb this into C1, and we can write this constant as C2. Therefore this becomes C1 plus C2 times V. So now when we write it as this, we can then say that over here C1 is P naught plus mass of pistons G over A plus F1 over A minus Ks over A square times V naught, and we can write down C2 as Ks over A square. Okay?
So
Hello,
actually,
sir. Sir, I have a doubt.
Yeah.
So here you said that x naught is the original length of the spring, and then you said that V naught will be the volume occupied by substance at
Mm,
relaxed condition. So
yes.
isn't V naught should be the volume of the above part, upper part?
See, V naught is, I mean, I'm calling it V naught, but V naught is like, how do I say? So suppose this is the base, and let's say this is the uh, rest position of the piston when the spring is in, what do you say, relaxed, when the spring is relaxed. So this is the distance x naught. Okay, so what is x naught times A gonna be? See, I think I know what you're thinking. You're thinking from here I'm measuring x. I've already mentioned we are measuring it upwards.
Oh, sorry, sir. Sorry, sir. I
Okay, yeah,
misunderstood that.
that is fine. All right.
Sir, excuse me, sir.
Yeah.
Sir, the spring force should be minus k times of x minus x naught, I guess.
See, I mean, let's put it this way: when it goes from x naught to x, when this is x, so now this spring is being compressed.
Okay, yes, sir.
Come on, guys, this is. I mean, HC Verma would be very angry at you guys. That's what I can
Sir,
say.
I did the
Of
same
course,
mistake. I took x from the
that's
top.
what I'm saying. So HC Verma would be not very pleased. So anyway, I mean, that happens. So the pressure is C1 plus C2 into V. Actually, you can do it from the top. Look, the physics is not gonna change. You can do it from here as well. You will still get a pressure which will be linearly related to volume. This is not dependent on the coordinate system. Okay, you can do it like that. This is not gonna be dependent on the coordinate system. You can just the constants will change. Okay, just the constants will change. This much you should be confident in saying. Obviously, it cannot depend. The physics of the problem should not depend on how you are defining the problem. I mean, final answer should also be the same. This much also I can guarantee you this. Final answer cannot depend on your choice, or rather, let me say the final correct answer should not depend on your choice of coordinate system. So, what does this look like? So, if I have pressure volume like this, so now we know that it varies linearly. This is I really need shortcuts for these things. Anyway, so it will vary like this. And so the intercept made with this and the slope of this curve are characterized completely by the two constants. So this is gonna be ks over a square, and this is gonna be c1. Basically, this is equal to c2, and this intercept is gonna be c1 when volume becomes 0. All right, so let us do a problem. Let us do a problem. So, yeah. Okay, before doing that problem, we've just skipped over one small step. So, if something which has a spring arrangement like this goes from state 1 to state 2, how much work is done? Work done in going from 1 to 2. So, W12 will obviously be integral 1 to 2 P dV, and this will be integral 1 to 2 C1 plus C2 V times dV, right? So what will be this? It will be C1. I mean, you can do this in various ways. So this whole square by 2C2 in going from 1 to 2. Can you write it like this? I mean, this is also
Yes, sir.
correct. I mean, there are various, ways of doing this. You can also write it as C1 V2 minus V1 plus C2 V2 square over 2. This is also correct, no problem. But when you just put in the limits, you can easily deduce that this integral has to be equal to the area under this curve, this straight line. And so what is this curve? I mean, what is the shape that is formed by this area under the curve? What is the area of a trapezium? Not a
So V2
trapezium.
minus C1
Sir, 1 by
into
2 is
P1 plus P2 by 2.
Very good. So it's half P1 plus P2 multiplied by V2 minus V1. Okay. So then this is literally that integral. You can always do it easily graphically rather than going to algebra. Okay, this is the work done. So now we are in a position to do a small problem. First, let me save this file. So this is what mechatronics. Okay, where did I? Okay, all the documents were in my home PC. I'll just make a folder. No problem. Thermodynamics 2022. That really sounds like Blade Runner 2047. So this is lecture on work. This is lecture on work. Where were we? Yeah. So let's say that a piston cylinder arrangement with a spring on top. Okay, so it contains half kg ammonia at minus 20 degrees Celsius with a quality of 25%. And this ammonia is heated to 20 degrees Celsius, at which point the volume is 1.41 times the initial volume, V final, or if I call this V2, is 1.41 times V1, whatever V1 is. So the question is, given this information, what is the final pressure? And the question is, what is the work produced? Okay, so this is the question. All right, so let us draw first the tentative schematic on the PV diagram. Okay. Yeah, well, so the first state is having a quality of 25%. So the first point is somewhere over here. And the corresponding isotherm, which is going to be this line. This isotherm is how much? What is the temperature of this isotherm?
Minus 20 degrees.
Minus
So
20.
this is the minus 20 degrees Celsius isotherm. Very good. And this has a quality, so we can precisely pinpoint where this particular point is. So using this, we should be able to figure out what the initial pressure is. What should be the initial pressure logically? Logically, the initial pressure P1 should be saturation pressure at minus 20 degrees Celsius for ammonia. Okay. So you can find this out. And it is given that initially you have half a kilogram of ammonia. So given that you know precisely what this state is, you will also be able to figure out what the specific volume of state 1 will be. And if you're able to figure out what the specific volume of state 1 is, you can find out the initial total volume. What is the formula? So the specific volume is equal to the volume per unit mass. And you know what the mass is, you can determine what the specific volume is. With the help of that, you are in a position to find out what the total volume is as well. Does that make sense? So over here we would have determined at the end of this, we would have determined what V1 would be. And because we would have determined what V1 would be, we know that V2 is simply 1.41 times V1. So we would have determined precisely the value of V2 as well. Once you would know the actual value of V2, you know that regardless of whether the piston is going up, coming down, staying there, whatever it is doing, You know that the control mass is always whatever ammonia is inside the system. So this control mass is always containing the same amount of ammonia. What does that mean? It means that even at this state 2, I will still have 0.5 kg of ammonia regardless of how the piston is moving. So I would have now the information about the total volume and the mass. Using this, I can easily determine what the specific volume of point 2 is, meaning I will know that point 2 will be somewhere over here. So this corresponds to specific volume V1, this corresponds to specific volume V2, because I can now determine what V2 is. And because it is at 20 degrees Celsius, the final state is at 20 degrees Celsius. Maybe this, I have drawn it a bit too far. What should I do? I should, in this particular PV plot, I should first draw the 20 degrees Celsius isotherm. So this isotherm is the 20 degree Celsius isotherm. Okay. And the intersection of V2 with the 20 degrees Celsius isotherm is the second point, and the straight line joining this is the actual process. The straight line which joins these two, maybe I can draw it with a different color. Maybe I'll draw it in red. This is the actual process. So because of this spring in the system, I am going from P1 V1 to P2 V2 along a linear line. How can I say it's a linear line? Because we have just derived that when you have a spring connected to the piston, the pressure will vary linearly with the volume. You cannot have any other kind of variation. All right. So we would have V2. We can easily find P2 because this second state is at 20 degrees Celsius. So if you know the temperature and if you know the specific volume, you are now in a position to figure out what the pressure also will be. So let's do these calculations. Let's see. So let me fire up ES, and the point will be that you must do the calculation using a table as well. In view of time, I am not doing that. So let me share my entire screen. You do realize that I'm not doing it because it would take a lot of time. That is the only reason. Huh? Don't think that
Yes, sir.
I have an intention of not showing you how to use a table. We have done enough problems for you to now easily figure out how to read values from a table, and you will have more confidence because once you start fetching values from a table, you have EES, so you can always verify whether whatever you have done is correct or not. So I've increased the font size. All right, so let's do it. So the first state, so let us say we know what T1 is, and T1 is minus 20 degrees Celsius. The quality X1 is what? It is 0.25. The mass in the system is equal to half a kilogram. All right. So first things first, we will figure out what the saturation pressure is. So I will say P1 is equal to pressure of ammonia at T equal to T1 and X equal to X1. I mean, I need not use X equal to X1. I'm repeating this because at all the points on this blue curve inside the saturation dome, I will get the same pressure. But still, for consistency, I'm doing it. Okay, where is the window? Here it is. So we get a saturation pressure of 190.1 kilopascal. What does that mean? That this pressure is 190.1 kilopascal. All right. So I will write VT1, that is the total volume initially, is equal to the specific volume at 1 multiplied by the mass. But I do not have the specific volume, so what can I do? I can say simply specific volume at state 1 is equal to volume. I can then copy this string of ammonia at T equal to T1, X equal to X1. Now I should have the total volume initially. Let me press calculate. So let me look at the array. So at point 1, VT1 is 0.07852. Okay. VT1 is, have I made some mistake somewhere? Specific volume is 0.15.
Yes, sir, it is.
No, it's correct, right? Yeah.
So the unit is meter cube, right?
Yes, the unit is meter cube. Now what should I do? I now know that V2 is 1.41 times V1. So I will say simply VT2 is 1.41 times VT1. This is correct. Now I can figure out what the specific volume at 2 is. The specific volume at 2 is equal to the total volume at state 2 divided by the mass. This is now the specific volume at point 2. Okay, I think the way of commenting is this. Yeah. So you can put comments in curly braces. This is now the specific volume at 2. All right, very good. Now what else do I have? I have that T2 is equal to 20 degrees Celsius. Perfect. Now with the help of V2 and T2, I now have two independent parameters. I can find out what P2 will be. So P2 will be pressure of ammonia at T equal to T2 and V equal to V2. Let me run this.
Sir, that will be V2, sir.
This will be V2.
So you didn't tell me.
That is why it threw an error as well. Okay. Now we have it. So V2 is 0.2241. This is the specific volume and this is the final volume. Okay. So the final pressure was how much? So the final pressure is 600.2 kilopascal, and in the book it is written as 600 kilopascal. So we are good. Pardon me. So what does it mean? It simply means, okay, I'm not able to maximize this for some reason. It means that this particular pressure is 600 kilopascal, 600.2 whatever. I mean, you get the point. So now what else was asked? We were asked to find out final pressure, which we have. We've gathered 5 marks. Very good. And the work produced. So the work produced is very simple. So the W12 will be equal to half times P1 plus P2 times VT2 minus VT1. So the work is 12.72. In the book it is given as 12.71 kilojoule. This is the work in kilojoule. Alternatively, I could have simply done this as well. This is also, I mean, you may need this. So W12 alternative is half times, so this stays here. So we will first say that we will find out the specific work. So instead of VT2 and VT1, we will have V2 minus V1. This is the specific work. So the specific work, when you multiply by the mass, you get the total work. Okay. So they are identical. Obviously they are identical. Okay. So this quantity is known as the specific work. Is specific work. Oh, oops. Okay. So in my lab PC, I will put this down as example 4.3 Sontag. I will share the file with you as well. Okay, did you understand? Oh, but I mean, of course, we must plot it as well. So we go to property plot. Wow, okay. We maximize this. So let's go to plots. We go to property plot. We go to ammonia. We go to PV diagram. We don't want ISO anything except T equal to -20 and T equal to +20. We want these isotherms on the PV plot. So we have the following plot. Now I will go to plot, overlay plot. On the x-axis, I will plot the specific volumes. On the y-axis, I will plot the pressures. And the line will be connected by means of a blue line. So I click on OK. And this is how the plot looks like. Okay, it's going from this point to this point. And why is the point so far to the right? I have already told this in one of the previous classes that this point is so far to the right, despite having a quality of 0.25 only, is because the x-axis scale is in log. Okay, it's in log, and that is why it looks like that. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
All right, so all good.
Sir, when our exam will start, sir, we can use E as an exam or we have to use.
So that is still being debated in not I wouldn't say it's debated, but that is still being discussed. So we will see, but you should be able to do it using both. Huh? You should be able to do it using both. You should not say that no, I cannot use a table. That's not justified at all. That is not justified at all. You must be able to do it using anything. Even if I give you a chart paper, you should be. This problem is very easily done using a property chart. If someone gave me this table, I can do this problem on this table as well, on this chart as well, this property plot as well. No problem. But this logic should be clear. This entire logic, this whatever you did first. See, this is the guiding principle. Without knowing how to deconstruct the problem to this particular, hand-drawn schematic. I'm not asking you for a full-blown schematic. No. I'm not asking you to do that. So one question which you should now be able to answer is, how did I know, how did we know that 2 is in superheated vapor? How do you know it's in superheated vapor?
Sir, temperature
I
increased
think
and volume is
we
also
calculated.
increased. So it would be,
Hmm?
So at T could
so as
actually find out the VG and then compare.
Very good, very good. So that is how you would do it. So what he said is correct. At 20 degrees Celsius, you can find out what the specific volume of this point is. And if the specific volume that you obtain using the total volume and the mass is larger than this, so Vg at 20 degrees Celsius, then you can safely say that you are in superheated vapor. Okay?
Yes, sir.
yes,
All
sir.
right. So we have run out of time, and tomorrow we will wrap up whatever remaining things over here are and start with first law. Next week we will try to do a lot of problems. So
Sir, sir, just one question. Sir, in this case, you analyzed by taking consideration that there is a spring, or in the other case, if there is like stop, then
We will come
like
to those problems. We will solve those kind of problems as well.
okay.
And in the mega playlist that I have shared, which none of you are watching, you are not giving me YouTube views, no problem. Please watch those. I have categorized all the problems as per chapters, chapter 3, 4, 5, so on. Please look into some of the problems that I've shared for chapter 3 in the mega playlist. I've put down the uh, playlist link in one of the previous chat of the general uh, thing that we have going on in Teams. I hope all of you have at least seen that link, even if you have
Yes,
not
sir.
opened it.
Yes, sir.
At least you
Yes,
know
sir.
that such a link exists. But bear in mind, you must also be able to use, to deduce the properties using a table. It will only be tantamount to requiring more time. A table, because you're doing it manually, it requires more time to see. But this logic is independent of you using a table, a chair, or whatever. Okay, this logic over here, that has nothing to do with using a table or plot or someone telling you the values. It's nothing to do with anything. Okay, so I will stop recording.